Today we will talk about ambiguity, but before that we will go through a definition of a simple programming language, then look at how ambiguity comes about naturally, and let us see. So, let us get back to our favorite grammar, our favorite context free grammar, which you have seen several times, is this, and let us look at the sentence that we generated. Using this grammar. So, now if you take a look at this, let us take a look at this sentence generation carefully. If your ultimate aim is to generate this sentence of this grammar, then let us look at how we have applied the productions or fired the productions. So, initially there was no alternative, we chose one out of three possibilities, right. There are three possibilities for S. S replaced by A, S replaced by V, S replaced by C, S replaced by an identifier. So, there are four possibilities, of which we chose one. In fact, if you are to generate this sentence, then there is really no other possibility you should take. Any other possibility will not give you this sentence. Okay. So, out of the four possible choices, we had to choose this. And then there was only one possibility for C, and we have chosen that. This here again, unless you chose this possibility A, you cannot generate this ultimate sentence. Okay. And for A, there is only one possibility, namely this. Now, you actually have two possibilities. Okay. We have chosen to fire this with S goes to B1, okay, which is essentially, which is essential in the sense that if you had to somehow produce this B1 in the end, you would have been forced to apply this S goes to B1. Okay. However, there was another possibility, that is that we could have ignored this and instead fired this. Okay. So, if we had chosen this S, then what would have happened is we could have got this step V first. So, these two steps would have been commuted. Okay. So, what we would have got is that if we had chosen this chosen to apply a production on this S, always keeping in mind that this is the ultimate sentence that we have to generate, what we would have got is not open bracket V and S, and then again we have the possibility of either firing this V or this S, okay, and we could have chosen any one. You could either replace this S by this B1 here, or we could have gone ahead with this V and replaced it by S or S. Okay. And then here again, now you would have here supposing you had chosen this V, you would have S or S, and this S would still be there. Then you have three possibilities of replacement, and you could choose any of them. Okay. So, so if you look at the derivation of a sentence, this particular order is not sacrosanct. Out of the various non-terminals in an intermediate sentence generation, you could have chosen any one and applied an appropriate production. Okay. So, there would be many such derivations of the same sentence, okay, depending upon the order in which you have chosen to apply productions in a sentence. In other words, what we are saying is whether you choose this or this, it really does not matter. So, the various derivations that you have just give you various orders either you, for example here we have not chosen any particular order, we could have chosen for example to always fire a production of the leftmost non-terminal symbol in an intermediate string. So here for example we have violated that, we have not chosen the leftmost. Okay. So here you might consider this derivation as one of several possible derivations of this sentence. Okay. So since we are talking about a context free grammar and the replacement of non-terminals by their right hand sides in the production rule, we are talking of something that is independent of context. So if there are several non-terminals, it really does not matter which non-terminal is chosen first for replacement, provided you can, so provided you choose the right one which will ultimately give you this sentence. So if you were to justify each of these steps in this derivation by which production you have applied, okay. So you could number these productions as 1, 2, 3, 4, 5, 6, 7, and you could write a justification which just tells you which production number you applied. Then even though then what you could do is essentially you could permute the order of applications of these productions. So for example in here you do not have much choice, but here as I said you have two possible choices, either an application of production 4 which is this, or an application of production 2 which is this, right. So you could have just permuted the order in which you apply these productions, but your intermediate sentences, your intermediate strings will not be the same, okay, but you could have permuted the order of application of these productions and you could have derived the same sentence. So what it means is that the application of productions for the derivation of sentences in a context free grammar can often be, need not be totally ordered. So there could, because of the context freeness of the grammar, there is an independence at an intermediate stage between the various non-terminals that you can choose to replace, right. So what it means is that there is nothing sacrosanct about this or this derivation. We could have got another derivation by just applying the same productions in a different order. So what it means is that these productions, because of their independence, what we can, however there is a certain amount of order. For example, you could never have applied any of these productions, let us say before applying this production, okay. You would never have any of these possibilities before applying this production, C goes to not S, if you are interested in generating this sentence. So given this sentence you would have to apply this before any of the others, but here you have a choice whether you want to replace this S or this S, but the actual production that you have to apply is still place specific. If you have to generate this B2 or B1, you have no alternative but to replace this S eventually, but whether you replace this S before you replace this S or after it does not matter, okay. So in any derivation, this independence between two or several other possible replacements that might be there gives you a partial ordering on the application of the productions, okay. So this partial ordering is really what is sacrosanct. So what does this partial ordering specify? This partial ordering specifies that if that there are certain productions which have to be applied in a certain order, but other productions need not be applied in the same order, they could be applied independent of each other. So, if you were to look at the various derivations possible for this sentence, we could take all those derivations and collapse them to give us the partial order, okay, coalesce them to actually see independence, look for independence and dependence. In fact, what we can do is we can draw a tree of exact dependencies. Okay. So, that tree is what is known as a parse tree. Yeah. So, if you were to take this, this is the same sentence that we have generated, okay, and what this tree tells us is what are the dependencies in the applications of the various productions. So, the root of a parse tree is always the start symbol. Okay. Now, in the generation of this sentence, the first production that was applied was S goes to C, which I have not written here, but you could for example write S goes to C as a production. Yeah. Then the next production was C goes to not S. Okay. So, that C goes to not S is what is here. So, the various terminal symbols, I mean I am looking upon the whole of not as a single symbol, okay, open parenthesis as a single symbol. Remember our convention that black denotes terminal symbols, the eventual strings that you generate will all be strings in black, strings of the language. The other colors denote certain abstractions. Yeah, right. So, the first production was S goes to C, C goes to not open parenthesis S close parenthesis. Then there was a production, then there was an application of S which yielded A, and that is this. This is an application of the production S yields A, and then you have this A yields open parenthesis S and S close parenthesis. And now we are here at this point, we are at the same position that we are here in the original sentence. Okay. And now the fact that you can choose this S first or this S does not really matter. Eventually, in whatever order you apply the productions for them, if you are interested in generating the sentence that you have generated, then the right hand S should go to a B1 and the left hand S should be expanded into a V. This V should be expanded into open parenthesis S or S close parenthesis, and it does not matter in which order you perform these two productions. The first one, if you are interested in generating this sentence, the first S should produce a B2 and the second S should produce a B1. Yeah. So, that is also the reason why I have used a brown color for the productions. Okay. So, we obtain a tree which we can call the parse tree, and the branches of, so the leaves of this tree are all terminal symbols. Notice that all the leaves of this tree are all black. So, if you read the tree, if you read the leaves from left to right, you get the sentence that you generated. So, you have not open parenthesis open parenthesis open parenthesis B2 or B1 close parenthesis and B1 close parenthesis, which is what this sentence is, right. So what we are most interested in is in the parse tree rather than in the actual derivation. Okay. So for any sentence we have a corresponding parse tree. For generating any sentence we do not necessarily have a unique derivation. Okay. So in this grammar that we have defined, for every sentence there is actually a unique parse tree. Yeah. So let's and parse trees are very important from the point of view of compiling, language implementation, from the point of view of specifying semantics, and it's the only thing that's really sacrosanct. And the fact that there are many orders of derivation for us, I mean there are many ways of traversing this parse tree, gives you several possible derivations. Yeah. So let's just summarize that briefly. So we can look upon a parse tree as presenting a partial order in the firing of productions. Yeah. And we can look upon a derivation of a sentence as just one of many possible traversals of the parse tree of the sentence. So for each sentence what we would like to have is a unique parse tree, not necessarily a unique derivation. What we want is a unique parse tree. Okay. So the traversal of the tree, depending on how you decide to traverse the tree, you have various possible derivations. So you can look upon a derivation as just a linearization of a partial order. Yeah. I think most of you are familiar with topological sorting, right. So for example, a topological sort just takes a partial order and linearizes it. You sort it so that you provide a linear order, a total order of all the elements such that the dependencies specified by the partial order are maintained, but where dependencies do not exist you might place them in any order you like. Okay. So a linearization of a tree always gives you a total order. Okay. And you can have, and in fact for partial orders it is also true that a partial order is completely defined by the set of all possible linearizations of the partial order. So essentially a parse tree is also completely specified, since it is a partial order, by the set of all possible derivations or traversals you can make of the parse tree. Yeah. So this is a fundamental property in the theory of partial orders, which is that you can look upon every partial order as actually a set consisting of all total orders of that set. Yeah. So as being completely defined by the set of all total orders. Okay. So now what actually, if the parse tree that we have presented is somewhat syntactical. Yeah. So it is syntactical in the sense that from the point of view of compiling or language implementation, it is all fine, in the sense that well, from the point of view of a language implementation, it does not really matter what is the nature of each of these terminal symbols. As far as it is concerned, it is some stream of symbols that are coming, and it just looks upon them as a stream of symbols. But any kind of language also has an implicit type of terminal symbols, which is clearly distinguished. For example, we make a clear distinction always between an identifier and an operator. Yeah. So for example, so So this we might call a concrete parse tree, where we make no distinctions at all between identifiers and operators. If they are terminal symbols, they are leaves of the parse tree. That is it. Okay. So what we are more often interested in is what might be called an abstract parse tree, where the same sentence you actually make a distinction between what are the operators and what are the operands. So if you look at this sentence that we have previously generated, if you look at this sentence, it is clear that our intention was to define a language of Boolean expressions, where the operators are not and or, and the operands are all those Boolean variables like b1, b2 and so on, right. So this clear distinction between operands and operators is what leads us to what we might call an abstract syntax tree. Yeah. So this syntax tree actually replaces the non-terminals. We have been, we have designed the language in such a way that we could easily elevate the operators to the intermediate nodes of this tree. We can talk of a root operator, which is not. We can talk of intermediate operators and or. Okay. So in an abstract syntax tree, the operators are always the intermediate nodes, okay, and the leaves are all the identifiers of the operands, right. And this is of course not something that's absolutely foolproof or anything, but when we talk about the distinction between operands and operators, we are saying that we are making a distinction between the various kinds of terminal symbols that are there in the parse tree, and we are elevating some of them. See, if you look at the ultimate language, the ultimate programming language that we are interested in, we are really not too interested in the non-terminal symbols. The concrete parts of the language, the real down to earth asphalt of the road, if you like, are all the terminal symbols. But those terminal symbols in any programming language have some meaning. There are some distinctions between what is an identifier, what is an operator. Okay. If you want to bring about this distinction, well, then what you are interested is not in this concrete syntax tree, but you are interested in what order should I apply the operators on the operands. In fact, if you look at this sentence, the reason why we included parenthesis, why we have parenthesis in all our mathematical language or anything, is to specify an order of application of operators on operands. Okay, right. So, and this is especially true for what might be called infix operators. It is not absolutely essential to have parenthesis, but you can see that otherwise we would have to have a uniform postfix notation or a uniform prefix notation if we have to avoid operators. Okay. So, in fact, every language construct can be regarded as an operator. Yeah. So essentially, if you are interested in giving meanings to languages, you are not interested in the concrete parse tree, but you are interested in the abstract syntax tree. Okay. If you look at the way you have done arithmetical calculations in school, you will see that you have actually, so remember that in an abstract syntax tree there are no brackets. Okay. Given an arbitrary expression, there are various ways of evaluating that expression. You can choose to evaluate one operand rather than the other, rather than another, unless there is an explicit dependency that you cannot evaluate one operand before the other. So, for example, if you have let us say an arithmetic expression like 3 multiplied by 5 plus 4 multiplied by 6. Yeah. In our normal arithmetic, there is an implicit order. This is the order. So, the abstract syntax tree of this is just the following. I mean, it's just this. You first apply multiplication. You cannot do this addition before doing both multiplications, but it does not matter in which order you do these two multiplications, and then you do the addition, right. So, all our evaluation mechanisms actually refer more to a syntax, to an abstract syntax tree than to the concrete parse tree of the expression. Yeah. So, we have to keep this in mind. So, I will often be using these abstract syntax trees. Once we cross syntax, I will be using only these abstract syntax trees. Yeah. So, let us keep that in mind. So, now keeping these things in mind, let us define a small programming language. Yeah, it's very simple. It's really amazingly simple that it's actually completely useless, if you like. Yeah. So, what does this programming language contain? It contains no declarations. It contains only Boolean variables and expressions. It contains the following commands: assignment, sequencing, a conditional, and a simple looping command. Yeah. And what I would like to do is to specify the syntax of this programming language, so that it clearly gives me all the possible syntactically valid programs in the language. I can generate, so that I can generate from the grammar all possible syntactically valid programs of the language. For anybody who has done some programming, it is clear that, I mean, but it's clear that you know what kinds of programs you are talking about, you know, in the sense that you know what would be syntactically valid, what would not be syntactically valid. But now there is a question of formalizing it and giving rules, production rules for the syntax in such a way that, for example, if you had to build a compiler or a translator for this language, you should be able to do it without any problems. Yeah. So, so in fact, if it were a course on programming, what I could do, since all of you know some programming or the other, is that I could just specify this much, and then we could start writing programs. Yeah. But for the purposes of translation and compilation, you require to specify things in some more detail. So, let me just summarize the construction, summarize my my coding of various constructs. So, this brown is part of the context free grammar notation, I mean the notation for productions. As I said, this brown looks very much like the bark of a tree. So, branches of parse trees and so on are coded in this color. The actual terminal symbols are of course in black. Yeah. In this, since we have two different kinds of entities, commands and Boolean expressions, I have used this dark brown for Boolean expressions and what might be called atomic commands. The assignment is an atomic command for which I have used light green. All other compound commands I use this light blue, and the actual program or a sentence of the language, if you like, is in dark brown. Yeah. So, this is whenever I change the change my color coding, I will inform you, but this is how I have defined the grammar. So, what we will do is we will define the grammar in a top down fashion. I mean, the best way to do anything is top down. So, let's look at it top down. So, let's look at this grammar. So, I have the start symbol. So, as far as I am concerned, I mean I am only interested in sentences of the language, and the sentences of this language are all programs. Okay. Unlike say a language like Pascal or something, there are no there is no program heading, and there are no let us say declarations, so on. So, what is a program in this language? So, this rule specifies that a program is any command. So, given any command is a full program of this language. Yeah. So, and what is a command of this language? Well, a command could be an atomic command, or it could be a sequence of 2 commands. Yeah. It could be a conditional command, or it could be a looping command. Okay. So, here I have used these brown bars to indicate that this actually is 4 productions: C arrow A, C arrow C semicolon C, C arrow if B then C else C phi, C arrow while B do C or. Yeah. Right. So, this bar actually specifies the various alternatives that you have for each non terminal symbol. Right. So, at the command level, or what in most of these imperative languages are called statement level, this is the thing. These are the various productions. We can look upon the definition of this programming language in terms of several levels, and this S gives you the production level, gives you the program level, and how the program level goes into the command level. Okay. This command level essentially tells you how it is. I have so far not specified what this atomic command A is, okay, but at this point it tells you how to form compound commands from simpler commands. So, it just says that any simple command is a command, and the sequencing of two well simple or compound commands, that is why it is in blue. This semicolon is a reserved word of the language, so it is in black. So, the sequence of 2 commands is a command in itself, and if B is a Boolean expression, then this conditional command, this conditional compound command might contain some compound commands inside it, and this while do command contains a Boolean expression and a possibly a compound command inside it. Yeah. Right. So, what it means is that as far as the grammar of commands is concerned, this B and this A are also terminal symbols of this level of the grammar specification. Yeah. So, but what we should do is, in order to get a complete definition, we should also look into these atomic commands and the Boolean expressions. So, let us look at the atomic command. There is only so since I specified that there is only assignment statement, there is only one atomic command. Yeah. So, the grammar or atomic commands is just of this form. Let us assume that V is a Boolean variable and B is a Boolean expression, then V assigned B is this atomic command. Okay. So, then let me look at the Boolean. So, the language of Boolean expressions, I am defining a different grammar just for variation. Okay. I could have used the grammar that I previously defined, but that grammar is a sort of a hodgepodge grammar. This is okay. So, let me look at this. So, for one thing, in that grammar there were the constants true and false were not there. Okay. So, the terminal true is a Boolean expression, the terminal false is a Boolean expression. Any Boolean variable is a Boolean expression. Okay, so these are the, so if you take the language of Boolean expressions alone as a separate entity, these are the terminal symbols of the language. Okay, and the next level specifies how do you make compound Boolean expressions from simpler Boolean expressions, right. So, if B is a Boolean expression, then not B is also a Boolean expression, and given two Boolean expressions, this is a Boolean expression and this is also a Boolean expression, and this is, so what I have used here, I have changed the grammar in the sense that here I have defined a fully parenthesized notation. Okay. So, I am for all Boolean expressions which are not atomic, these are the atoms of the Boolean expression language. For all Boolean expressions that are not atomic, I have enclosed them in parentheses. Yeah. Right. So, now supposing we did not do that, okay, supposing instead we define this grammar, consider, so I have gotten rid of true and false. Now, just consider this grammar. Supposing we did get such a, we defined such a grammar without parenthesis, okay. Then consider this sentence. This sentence is generated by this grammar. It is very easy to give a derivation for that, but not just that. This sentence can actually be derived in two different ways. Yeah. So, look at this sentence, V1 or V2 and V3, and this is my grammar. So, what I could do is I could apply the B or B rule and derive this. I could choose to expand this and get, since my first symbol has to be V1, I do not really have any other alternative maybe. So, I got V1 or B, then I can choose to expand this, replace this by B and B, and V1 or V2 and B. I can choose to expand this and replace it by V2, and then I can choose to expand this and get this. Yeah, right. Now, I could also make a different derivation. So, for example, I can decide to apply this B and B here, yeah, and I can choose to expand this and give me V1. Oh, what did I do? I chose to expand this and replace it by B or B. Then I chose to expand this and replace it by V1. Then I chose to expand this, replace it by V2. Then I choose to expand this and replace it by V3. Yeah, and I get the same sentence, right? But yeah,
there are no brackets in this.
There are no brackets in the language.
Then how we have to know that it is V1 or V2?
Right. So that's the point. So that's what ambiguity is all about. Yeah. So the point is that if you were to look at the way in which these productions have been done, then and the way in which these productions have been done, here AND is a root operator. So if you were to look at the abstract syntax tree, then and is a root operator, and below that is an or, and this is the abstract syntax tree that you get. Yeah, I have chosen to just give you the abstract syntax tree, but you could, for example, take the concrete parse tree also of this derivation. Okay. Now, if you were to look at the abstract syntax tree of the other derivation, there or is the root operator and comes inside, and if you look at these two trees, you can see that they are both actually different. Okay. There are not just two different derivations of the same sentence, there are two different derivations with different syntax trees. Yeah, and the two different syntax trees actually affect how you can specify the meaning of this language. So, for example, if V1 had the value true and V1 and V2 had the values true and V3 were false, then the evaluation of this syntax tree would give you a value of true, and the evaluation of this syntax tree would give you a value of false. Okay. So, if you look upon syntax as ultimately having to specify a meaning, then what you would like is a unique meaning to be specified. In that sense, this grammar, for example, falls short of being an adequate representation of a unique expression language, an expression language with unique meanings. Yeah. So, we call such a grammar ambiguous. It is called syntactically ambiguous, but the syntax is really a via media in which you are going to specify semantics. It is only an initial handle for the specification of semantics. So let us look at this grammar. A grammar is ambiguous if there exists a sentence in the language with more than one parse tree. Okay. Right. So ambiguity is an important constraint in the sense that it's not just that there are just two different derivations. It is that there are two different parse trees. Those parse trees are important both from the point of view of translating, which means running programs. I mean, if you're looking at the problem of compiling, then you're really looking at the problem of executing programs in order to get meanings. So it's necessary for a program to be interpreted in exactly one way. I mean, and actually the compiler for that program and the user of that programming language should both come to an agreement on how that program is to be interpreted. Right? So ambiguity has very serious consequences in specifying the meanings, which means the execution behavior of programs. Right? And actually a lot of our programming languages, for example, I have a lot of our programming languages actually do have ambiguity. So the programming language that we have defined is totally unambiguous. Yeah. This grammar specifies a language in which there is absolutely no ambiguity. Okay. There is exactly one parse tree for every sentence in the language. Now, if you were to look at languages like Pascal, so one reason why, so in the expression language there is always ambiguity in most languages, but that's because the expression language allows you to use normal mathematical notation. Okay. So for example, it allows you to specify various things with an implicit order of evaluation. So, if you look at our these expressions, for example, it allows you, our normal mathematical notation allows you to specify this expression without any parenthesis, where it is implicitly assumed that the syntax tree for this expression, if you remove the parenthesis, is still going to be this and nothing else. For example, it does, if you remove the parenthesis, there is absolutely no reason except normal mathematical convention why you can't have a syntax tree of this form. There is absolutely no reason why, except for normal mathematical convention, there is absolutely no reason why you should not construct such a syntax tree, supposing I remove these parentheses. Okay. But it is just that our mathematical convention says that, well, there is a precedence of operations which ensures that multiplication is done first and addition is done later. So, if there is ambiguity, if there is syntactic ambiguity, then the order of evaluation should be that multiplication should precede addition. Otherwise, the order of evaluation is as specified by the parenthesis. Okay. So, since this is our normal mathematical notation, most programming languages actually implement this. Okay. There are also at the command level too, there are syntactic ambiguities, for example, in languages like Pascal. One is what is known as the dangling else problem. Yeah. So, if you look at the difference between our conditional, the conditional that we have defined, and Pascal, is that firstly we do not have both an if then and an if then else construct. We have a perfect bracketing between these. For example, if our conditional construct has a perfect bracketing, there is an if with a phi and a while do with an or. Okay. So, there is no possibility of ambiguity except in the case of one construct. What is that? No. Where is the ambiguity? Where is the ambiguity?
We have a nested if then else structure.
This grammar does not provide ambiguity for that. It is totally unambiguous for that, but there is still one place where there is ambiguity. The sequencing is ambiguous. So, think about it, we will come back to it later.